let me practice this. Okay, so I'll start with the basic Diophantine problems. You look at a polynomial with f of x1, xn with integral coefficients, and then you ask whether you look at this equation, and you want some technique to decide if there are solutions for these equations with the xi integers. Okay. Or you're very happy if you can decide whether there are solutions with xi rational numbers. Okay, if you take homogeneous polynomials, the problems are essentially the same. You ask for primitive solutions, that is, you want the x1, xn to be integers co-prime as a whole. Okay. And it's a question in rationals or in integers, it's then the same problem. In the language of schemes, so I'm supposed to be elementary, but I'd say schemes from time to time. When it has a scheme x over z, this is really a scheme over z, if you give an equation like this with coefficients in z, and coefficients in q will have a scheme over q. And then you want to decide, so this is some very convenient notation. X of z is a set of solutions with coordinates in z, and x of q is a set of solutions with coordinates in q. And you want to decide whether there are some such points. Okay, so there are immediate conditions which which have to be satisfied. So, for instance, there are very stupid cases. If I look at x squared plus y squared plus z squared equals 0, then there's no solution, no non-trivial solution, because everything has to be positive, so the only solution is 0, 0, 0. But if I look at this one, well, there are real solutions, but you see very easily that there are no non-trivial solutions, that is different from 0, 0, 0, because you look at congruencies modulo 9. Okay, so you say, well, let me do this very quickly, if you've never seen this before. So suppose you have a solution for x, y, z co-prime. For this solution, you reduce modulo 3, you find x squared plus y squared is 0 mod 3, but because the only square mod 3 is plus 1, that forces 3 to divide x and y, and then 3 divides x and y, but then 9 divides x squared plus y squared, divides 3z squared, therefore 3 divides z, and then you have a contradiction, because 3 divides x and y and z. Okay? So there's a basic argument. You can also do this argument by congruency modulo 4. Okay? Okay. Now, so this, you have this necessary condition for the existence of solution is that no congruence must be in the way. Okay? And since Hensel, so this is the end of the beginning of the 20th century, we know that this condition about congruences translates as a condition in terms of fields. So instead of looking modulo p to p squared, pq, p to the n, you create some field, qp, which has a ring of integers zp, and you ask for the set of solutions in zp, or the set of solutions in qp. Okay? So this basic notion of qp, which is so in the same way as the reals are the completions of q with respect to the absolute value, the p-adics are the completion of q with respect to a p-adic absolute value. So q, I mean, people in number theory view q as equipped with this various bigger field. Q sits in R, but also sits in each qp for each prime p. Okay. And then, as I said, you have this other condition for existence of rational solutions. You want solutions in the reals. Okay. So if you're given, let me skip the separated scheme of, this is to be honest, scheme of finite type of a z or of a q, what you get is that the set of integral solutions you're interested in sits in this product for all the primes p of the local solution. The solution is coefficient in zp, which sits itself in something called the Adel of x, which I will not define. And then the rational points sit in the Adel points of x over q, which sits in the product of the x of qp. So the Adels is something which sits in product of x of qp, but which is a bit better. You want that at almost all prime p, the coordinates are integers. Okay? And so these inclusions summarize all the possible congruence conditions you could think of for a given x, that is for a given system of equations. Okay? So for p equals infinity, by convention we set z infinity equals q infinity equals the reals, the usual reals. Okay, and the set I define here, the set of Adels, it's the families of local points which are integral for almost all p. When the value is projective, that is in terms of equation, if you're given homogeneous forms, then in fact there's no difference between the Adels and the product of the x of qp. Okay, and so a fact is that whether this set and this set are not empty, and again these ones, that you can decide, given any equation, you give me an equation, after a finite amount of time, I can tell you, yes, this is empty or this is not empty. Okay? But the problem is we're interested in this smaller set. Okay, so there are cases where the solution is good. That is, there are cases where if this set is not empty, then this one also is not empty. Similarly, there are cases where if this set here is not empty, in fact, if this one is not empty, then this one is not empty. So the most famous case, well, the historical case is the theorem by Legendre in 1785. So you take an integral quadratic form, q of x, y, z. If you want, you think simply of ax squared plus by squared plus cz squared equals 0. Okay? You can think it in diagonal terms. Okay. If the equation has solution in each zp, including the reals, then it has a non-trivial solution in z. Okay? So you just have to look at congruence conditions, and in fact find them in A, as I said, and then you can decide whether there's a solution in integers. Okay? And the proof by Legendre uses the geometry of numbers. In fact, it's a very nice proof. That is, you get an upper estimate for the size of the solution. So that you actually prove that if the congruence conditions are satisfied, then there's a solution in x, y, z, where x, y, z integer at most equal to some simple function of the coefficients, so that you can give it to a computer and then decide, look in this box, search for a solution. In fact, you can ignore the conclusion in that case, because you know that if there's a solution, it has to sit in this box, so you could put it in a computer. But it takes, well, by hand, it takes more time, let's say. By computer, it probably takes less time to use the second method. Okay, so now the various proofs of this theorem of Legendre, if you look at the book, typically the book by Brauer-Manin and Safarevich, some basic books in algebraic number theory, you find it's something curious, that one doesn't use the full hypothesis that there are solutions in each ZP and R. So for instance, you can forget the hypothesis that there's a real solution. If all the congruence conditions are satisfied, well, there must be a solution in the reals automatically. Okay, so it's quite strange. So it's imposed by the condition. If you put this condition is imposed by all the finite ones. Okay, and in fact, this fact that all conditions but one imply the last one led at some point to the idea of the law of quadratic reciprocity, which is a basic theorem in number theory, which I remind you what it is. So if you take an odd prime, and you take an integer which is prime to p, you define the Legendre symbol, a over p, which is plus or minus 1, in the following manner. You decide that a over p is 1 if a is a square modulo p, if a can be written as b square mod p. Otherwise, you put minus 1. Right? And then the remarkable law is that if you take two odd primes, there's a relation between p over q, the Legendre symbol of p at q, and the Legendre symbol of q at p. And it is given by simply this minus 1 to the power of p minus 1 over 2, q minus 1 over 2. And this was conjectured by Euler and Legendre. In fact, Legendre partly on this phenomena that there was all conditions but one implied the last one. And it was proved by Gauss. And Legendre always claimed that he had a proof, but in fact he didn't have a proof. There was a mistake in the proof and so on. But anyway, so this is a theorem. And it's the basis of, so when people, for instance, when you ask people in automorphic function theory what they are doing, when they manage to give you a clean-cut answer, they say, we're trying to get the utmost generalization of the law of quadratic reciprocity. It's quite a fine answer for that question. Okay, so this result of Legendre for ternary quadratic forms, that is quadratic forms in 3 variables, was extended by Minkowski over the rationals and by Hasse over number fields. So the statement is, let me stick to the integers for simplicity in this talk. Take n at least 2 and take a quadratic form, an integral quadratic form. If this equation q of x1, xn is 0 has non-trivial solution in all zp and also in the reals, then it has a non-trivial solution in z. Okay? So the theorem for 3 variables extends to the theorem for as many variables as you want. But here you really have to impose solutions at all places, at all completions. Okay? So in Hasse's proof, if you look, in fact, there are various proofs, but in Hasse's proof, 1924, I think, the main ingredient occurs when you use the theorem for 3 variables to prove the theorem for 4 variables. This is the difficult step. Indeed, the proof combines Dirichlet's theorem and primes and arithmetic progression with the law of quadratic reciprocity. So Dirichlet's theorem in primes and arithmetic progression says that if you take A and B integers, co-prime, let's say A positive, there are infinite primes of the shape AN plus B. So the polynomial AX plus B represents infinite primes. We'll come back to this kind of statement later. Okay, and so these were statements. These were local global principle. That is, if we have solutions in all the completions, Q, P, and R, then we have solutions in Q. But you can ask for similar questions with Z, P, and Z. Okay. It's okay if I say Z rather than Z.
It's okay.
I was brought up in Britain. Okay. So for integral points, there are some famous cases. So one famous case, which is normally not stated like this, is the famous result that if you take a prime congruent to 1 mod 4, it is a sum of two squares of integers. And if you think of the equation P equals x squared plus y squared, the congruence condition boil down to this congruence here. The other ones are automatic. Okay. So another one is if you take an integer, you ask yourself whether this positive integer, say, is the sum of three squares of integers. Then if the equation has solutions in R and in Z2, then it has solutions in Z. So the condition in R is saying that n is positive, and the condition in Z2, you can say it in very concrete terms, in terms of the fact that basically bad elements are the ones which are of the shape 8m plus 7 times some power of 2. Okay? So this is a way of phrasing this result of Legendre and Gauss. And then there's another famous one, which is Lagrange's result, that any positive integer is the sum of four squares of integers. So here there are no local conditions except the positivity condition. I mean, the local conditions are automatic. If you look for congruence obstruction, you won't find any congruence obstruction. So the only condition here is that n be positive, and then it is indeed a sum of four squares. So any positive integer is a sum of four squares. Right? So the basic question I want to address in this talk is that are there such local global theorems, which are called Hasse principles, or appropriate substitutes for other classes of schemes? Now, in let's say when 30 or 40 years ago, if you looked at books about who explained the Hasse principle for quadratic forms, invariably they would end up with saying, well, it is desperate to find any other case where this holds. Okay? And then they produce some examples, which very often were, from the point of view of modern algebraic geometry, very stupid, because there were examples where, say over Q, where the solutions in one of the completions were singular solutions. So there were very few solutions in one completion. And it happened that these very few were not rational. So there were no solution at all. But this is not a nice question to ask. You have to, from the point of view of modern algebraic geometry, you must ask for non-singular local solutions. That is, non-singular in the sense of differential geometry. I mean, if you have one solution, you want the variety to be analytically isomorphic to Rn or to Qpn, for that matter. Okay. So, in fact, there were cases where the Hasse principle was proved. And so it was proved for rational points for projective homogeneous spaces of connected linear algebraic groups. So a linear algebraic group is a subvariety of GLN which has a group structure. Okay? And then if you have a variety which is homogeneous space, that is, you have a group acting on it in the sense of algebraic geometry, and which acts transitively on the complex points. This is the meaning of projective. It doesn't mean projective on the rational points, but on the complex points. Then, in fact, the Hasse principle holds for these varieties. And this is the outcome of a long series of works starting before around 1938, I think, and Harder, and then Chernousov, in fact, to complete this over a period of 30 or 40 years. Okay. And then the other, so this is one class of varieties for which we had a principle, which extends the case of quadrics, because quadrics, of course, are homogeneous spaces of the special orthogonal group. So, but these are very special varieties. You have this extremely rich group structure here. So my problem is to see whether outside of this world there is something. The other big class of varieties for which a local global principle was proved is the case of projective hypersurfaces, like we had quadrics, with the number of variables quite big with respect to D. And already here, you want the singular locus not to be too big. Singular locus is the place where, well, where the variety is singular, okay, in the sense of complex geometry. Okay? And for this, there is the circle method, which goes back to Hardy Littlewood in Britain, and it's a very British activity. Okay? Okay? All these people are from Britain. And what happens is that this method is very powerful. It's an analytic method. It's analytic number theory. The defect it has is that it will give you results for a number of variables which is much bigger than what you hope is the real truth. So typically you would hope that with some conditions you would be fine if the number of variables is bigger than, say, d plus 1. And they get something like d squared log d. But still, it's encouraging. There are some classes of varieties for which you have a method to decide if there is an integral point. Okay? And then there has a principle for, this was for rational points. And for integral points, this principle holds for the representation of an integer by an indefinite integral quadratic form in at least 4 variables. So just before, we had a representation of an integer as a sum of 4 squares. So this is a definite form. So it's positive of the reals. Now, the representation of an integer by a positive definite form actually is a very difficult problem. It turns out the case of 4 squares is very special. But if you look at ax squared plus by squared plus cz squared plus dt squared, then it is very hard to decide what are the integers which are represented by this form. But when the form has some negative sign, plus and minus, when it's not positive, when it's indefinite, then in fact there is a local global principle due to Heichler and Kneser. Okay, and the last case is represented by an integer by certain integral forms with n big with respect to the degree, and it's the same technique as this one. So it also says something about integral points. So the circle method. Okay, so these are sort of classical results. Okay. But okay, so many examples show that the Hasse principle in general does not hold. Okay, and most textbooks stop here, and quite often they stop with these stupid counterexamples, I call them, where it's just some singularity problem. Okay? But there are better counterexamples. And so, in fact, going back to 1934, I think, you see the fact that a quadratic form in 3 variables has satisfied the local global principle can be expressed in a different fashion. You can say that if you have a quadratic extension of Q, if an element is a norm at all completion, then it is a norm of the rational. And you can ask, well, okay, this is a quadratic extension, but then what about other field extension? If something is a norm, I have a field extension of Q. If I have an element which locally at the completion is a norm, is it a norm? So in fact, the class field theory showed that the answer is yes if the extension is cyclic. So if it's Galois with a cyclic Galois group, then the answer is yes. But as early as 1934, Hasse and Witt realized that if you take, for instance, a Galois extension with group Z mod 2 cross Z mod 2, the first non-trivial example, then in fact it doesn't work. You have counterexamples. Okay? And Serre also produced examples with groups which are more complicated than these groups, than this norm 1 example. Okay? So this is one class of interesting counterexamples. A second class of interesting counterexamples is curves of genus 1, which are two-state forms of elliptic curves. So everybody knows about elliptic curves, you know, y squared equals x minus 1, x minus 2, x minus 3. But you have curves which over C look like this, but over Q do not look like this. For instance, this thing here, over some field extension, you can reduce it to y squared equals polynomial of the 3rd degree, but you cannot do it over Q. And in this curve here has, and this is a thing that goes back to 1940, this curve here has solutions in all the completions of Q, but not in Q. So another class of varieties for which there were counterexamples were found, but later, is the case of surfaces with a pencil of conics. You see, conics, that is ternary quadratic forms. Ternary quadratic form defines a conic. Conics satisfy the Hasse principle. You could ask, if I have a 1-parameter family of conics, I look at the total space. Does it satisfy the Hasse principle? Well, the answer is no. So you have 1-parameter family. T is the parameter of conics, like this one, x squared plus y squared plus 3 minus t squared, 2 minus t squared z squared. This thing has solutions in all the completions, non-singular solutions in all the completions of Q, but not in Q. This was 1970. And before that, there was a very tantalizing case, because cubic curves, of course, have been much studied. So you could ask about forms in 4 variables. And so there's an example of Swindler, which is more complicated for a cubic surface, and there's a famous example of Castles and Guy with a diagonal cubic form. 5, 9, 10, 12 are the coefficients. And if you look at these coefficients, maybe I don't know whether I will come back to this, but let me say it already. You can see something special about this, namely each prime, which occurs in one slot, occurs in another slot. So 5 is here, 3 is here and there, 2 is here and there. So this is a rather special equation. I hope I'll come back to this. Okay, so there are also counterexamples to that's a principle for integral points. Okay, remember the title of my talk we had integral points as well. So a classical question is, given an integral binary quadratic form, so you're just two variables, think of ax squared plus by squared or x squared plus bxy plus cy squared, and an integer n, do you have a technique to decide if n is represented by this form over z? Okay. This is very classic. It goes back to Gauss, Legendre. I mean, all these people were very interested in this problem. Okay. And now, congruencies do not suffice. In fact, you can find very trivial examples. If you take, you say, I didn't say about the quadratic form, I didn't say whether it was reducible over Q or not. So you can give examples like this. You look at 23 equals x plus 7y. And you will very easily decide that congruencies conditions are satisfied, just check it. But then, because there are not many ways to factorize 23 as a product of two things, you see that there are no solutions in Z. So already here you have a counterexample to the answer principle for binary forms, for representing an integer by a binary form. And you can also do quite easy examples like this one, which clearly has no integer solution, but has solutions in all the completions of Z. Okay? And then you have more subtle examples like this one, where it's not obvious a priori that there's no solution in Z. Okay? And this one, in fact, one key to proving that there's no solution in Z is factorizing this, rewriting it as this square on the right-hand side and this product of two factors on the left-hand side. I hope I'll come back to what's behind this later. Okay, so the proof that there are no integral solution in the first two cases is elementary. Okay, you use divisible arguments and size arguments. Now you use also the fact that the only units in Z are plus or minus 1. So if you were asking the same problem over a number field, you'd be in trouble, even for a form which is factor of two linear forms. Okay, so for an equation like n equals Lxy and n linear, there's a finite process over Z to decide this. Okay, so here's the first comment. Yeah? Now, what about n equals q of xy when q is irreducible? And now let me make a bit of propaganda if you're interested in number theory, in a beautiful book by David Cox called Primes of the form x squared plus ny squared, which starts with the observation that any course in number theory, it's a graduate course, starts with proving that precisely any prime p congruent to 1 mod 4 is the sum of two squares. And he says, well, what about if I take x squared plus ny squared? Can you tell me which prime are of the shape x squared plus ny squared? And he shows, his book is really magnificent. There are three parts. There's an elementary part and historical part. And then there's classical number, well, there's class theory. And then at the end, there is complex multiplication. It's really, it's gorgeous place. It's an amazing book. Anyway, so here is one example from this book. You take a prime which is going to 1 mod 3, and you ask, you ask whether it can be represented by x squared plus 27y squared. So the classical case which had been discussed is x squared plus 3y squared. But what about x squared plus 27y squared? Okay. Now, if q is congruent to 1 mod 3, this has solutions in all the congruence conditions are satisfied. But it has solutions in integers if and if a strange condition 2 is a cube in the finite field FQ. So it's really not at all obvious, and it was conjectured by Euler, who couldn't prove it, and proved by Gauss. So it's a very strange thing that you have this cubic extension, this cubic FQ cubic root of 2, which appears here. Okay, so around 1970, there were quite a few counterexamples to the Isor principle. That is, examples of varieties which had solutions in all the QP but not in Q. Okay. And if you looked at all these, you could see that at some point in the proof that there are no rational points, the law of quadratic reciprocity, or sometimes a higher reciprocity law, was used in the proof. And then in 1970, Manin showed how you can put nearly all the known counterexamples at that time into a common mold. And this is what I want to explain. This is the Brauer-Manin obstruction to Dasser principle. So for the time being, I'm discussing rational points. We'll come to integral points later. So for this, I have to explain a bit of algebra. What is the Brauer group of a variety? But to start, I start with the simplest variety, which is a spectrum of a field. So the Brauer field. You take a field, and you let K bar be a separable closure of K, so maximal separable extension. And say for simplicity, assume the characteristic is not 2, and take 2 elements which are non-zero in the field. Now you can define a 4-dimensional algebra by the relation you add variables, so to say I and j, and you impose the condition I square equals A, j square equals B, and ij anti-commutes with ji. Okay? And that gives you a 4-dimensional algebra, which is a twisted form of 2 by 2 matrices. That is, if you extend the scalar from K to K bar, you actually recover 2 by 2 matrices. And in the case when take K equals R and A equals B equals -1, this is something everybody knows, namely the Hamilton quaternions. So the Hamilton quaternions are something over the rails. You can create such objects over any field and study them. And quite generally, a finite-dimensional K algebra is called a central simple algebra. This was the German term when it was invented. If there exists an integer n such that if you change the ground field, you get something isomorphic to matrices. So it's like matrices, but it's not matrices. It's not isomorphic to matrices over K, but if you extend the ground field, it becomes isomorphic to matrices. And then, just like Mn times M is isomorphic to M and M, if you tensor product of 2 simple central simple K algebra, you still get a central simple K algebra. Then you make a definition that 2 such algebras are equivalent if there is some isomorphism like this. So tensor product gives rise to, you can take you take the set of equivalence classes of central simple algebra. You look at tensor product. A priori, it's just a monoid structure, but actually it's an abelian group. That is, in particular, there is an inverse, which is very easy to define. It's the opposite algebra. You take the multiplication x, y. The new one is multiplication of y, and x. Okay. And that object, which puts together all the possible central simple algebra of K, is what Richard Brauer invented, and also Albert, is the Brauer of K. So it's a group that puts together all the possible central simple algebra which you have. And in fact, if you have 2 central simple algebra A and B, which have the same class in the Brauer group, then in fact they satisfy something like this. Okay, so it really classifies the central simple algebra. Now, the quaternion algebra, the Hamilton quaternion, are the only non-trivial central simple algebra over the rails. And this is expressed by the fact that the Brauer of R is Z mod 2. If you look at the p-adix, class field theory computes what all the possible central simple algebra over QPR, and when finds Brauer of QP is Q mod Z. Again, this is something which goes back to 1935, 1940. Okay. It was, yeah. Okay. And then there's this basic theorem of class field theory, which gives a relation between the Brauer group of Q, what happens over the rationals for central simple algebra, and what happens over the various completions for the central simple algebra. And it's a short exact sequence. That is, you have this isomorphism here, so you have maps from Brauer of QP to Q mod Z. You can, if you take direct sum, you can send it to Q mod Z by taking the sum. This is obviously surjective. The rational ones, for almost all P, they're 0, so you land in the direct sum. But then here you have 2 pieces of information. One piece is that this map is injective. That is, if a central simple algebra is trivial over HQP, then it is trivial over Q. That's a local global principle. That's as a principle. Okay? And there's another one, which is the composite is 0 here. And this is a generalization of the law of quadratic reciprocity. So this is the first generalization and a great generalization of the law of quadratic reciprocity achieved by people who developed class field theory. And there's one more piece of information, is that if you take invariance with sum to 0, actually there is some global object behind. And that's also quite striking. Okay. So this formula sum ABP contains a special case, the law of quadratic reciprocity. And so I don't want to, this is, well, let me skip this one. well, okay, I can, so if I have a conic, the fact is that the conic of a field K has a rational point if only the class of the coordinate algebra AB vanishes. So this is one class, one case where the existence of a rational point on a variety just translates as some element in the group is 0, which is much nicer from the point of view of mathematics. Okay? And so Legends' theorem in this context says that if each Fourier prime P, ABP is in Z mod 2 vanishes, then in fact AB is 0. So this is exactly the statement we had before. Okay, and then here we see from the sum equals 0, we see that the vanishing of ABP for all P but 1, except possibly 1, guarantees the vanishing of the last one, because the sum is 0. So if all of them are 0 but 1, well, the last one is 0. Okay. So now this was the Brauer group of a field. Now let's look at the Brauer group of a scheme or of a variety, if you don't like the word scheme. So you have on a vector space, on a field, you have the notion of vector space. On a ring, you have the notion of so a commutative ring, you have the notion of a projective module, so a finite rank, which is the generalization of vector space. Okay? On a field, you have central simple algebra. Well, on a commutative ring, you have the notion of Azuma algebra. This is the natural extension. Okay, so Azuma algebra over a scheme are the natural generalization of central simple algebras, there's an L missing here, over a field. Okay. And one can introduce an equivalence relation on Azuma algebra, just as we did for a central simple algebra over a field, and that gives rise to a group which is the Brauer of X. And the construction is functorial in X. Okay, that's an important point. That is, if you have a scheme over ring R, you can evaluate on the R points. So you must think that you have your, it's like a function. If you have a variety and a point, you have a function on the variety, you can evaluate at the point. Well, you have the variety, you have the Azuma algebra, you have a point, you evaluate at this point. And you get an Azuma algebra over the field in that case. Okay, now let me explain what Manin discovered, which is a very simple fact. In fact, he had an idea how to unify various complicated arguments which are in literature, which were just subsumed into one argument. Okay? And so what Manin noticed, it's a theorem, but basically it's a proposition. If you take a projective variety of rationals, and you look at the Adel points, which in this case is simply the product of, for all P of the X of QP. Now you can define a pairing between the Adel points and the Brauer of X, because I said you could evaluate any alpha and Brauer of X at a point MP. Now a point MP is a point X of QP, so if I evaluate, I get an element Brauer of QP, and then I can, that is, I'm in Q mod Z. So if I have a family MP, I can evaluate alpha and the family MP by taking the sum, and I get an element in Q mod Z. And the statement is that if I look at a rational point viewed in the Adels, in fact it lies in the subset, the elements which are orthogonal to the Brauer group with respect to this pairing. So inside X of AQ, which was the obvious congruence condition, you have defined a subset in which the rational points have to lie. So that in fact, all the counter, maybe this is what I said in the next slide, is that all the counterexamples which were available at the time to the Asser principle, they were of the shape that this set was not empty, but this one was empty. So therefore, there was no rational point. Okay, and so it's summarized in 5 lines, various arguments, which each time people say, oh, I tried this, I tried that, and the problem is that once you have said, the point is that when you have said that, you know, if you look at another type of equation, you know what you should do if you want to decide this set is not empty. Well, first of all, this set, it was not clear what this set was. Now we know what this obstruction is. That is, if you're confronted with a new type of equation, if you want to use the same kind of method which these people had been using, you don't ask yourself, oh, shall I use the law of quadratic reciprocity? Shall I use the law of cubic reciprocity? You know, you have to compute the Brauer of X and compute the pairing. Okay, it may be difficult, but this is exactly what you have to do. Okay, and there's an integral version of this which has been discussed recently, where it's very similar. You take integral, so this time you have a scheme over Z, so equation with integral coefficients. You look at the solutions in ZP, and you can pair it with the Brauer of X over Q. In fact, it's better to do that. And then again, the set of integral points lies in a subset of the product of the local points of ZP, which is the part which is orthogonal to the Brauer group. Okay? And again, this set might be a proper subset of that one. Okay? So there's a technical point, which is that it's much better to pair with the Brauer of X over Q than the Brauer of X itself. This group might be bigger, so it might impose more condition. But the pairing is still defined with that group. Okay, after some work, it turned out that all the counterexamples to the Husserl principle for rational points, which were known until 1970, and in fact until 1999, could be explained by the Brauer-Manin obstruction. So there was, in fact, there was one case which resisted Manin at the time, which was the case of diagonal cubic forms, which was quite complicated. In fact, later, Kanevsky, Sansuk, and I, we computed the Brauer-Manin obstruction for these diagonal cubic surfaces. And we proved actually that the only case when there may be a counterexample is when you have this phenomenon that there's a prime, any prime which occurs in the coefficient has to appear in two slots. Okay. So one started looking for classes of smooth projective connected varieties over Q, for which the Brauer-Manin obstruction is the only one. That is, you ask, if this subset is not empty of the Adels, does that imply that there are rational points? So okay, congruence conditions are not enough. But this new condition, which has been coined by Manin, is it enough to decide if there's a rational point? Okay. Okay. And there's a subsidiary question, which is to check whether there's a final decision procedure to decide whether this set is not empty. And it's a difficult problem. Okay. So this implication, so this question whether this new condition is enough to decide whether there's a rational point has been answered positively in a couple of cases. Okay, so this has been solved for varieties which are essentially equivalent to a homogeneous space of a connected linear algebraic group with some technical condition that the geometric isomorphic groups are connected. Now the difference between this case and what we saw before I mentioned the case of homogeneous varieties which were projective at the same time. Now they need not be projective. Okay? So it's free, you have a projective variety and you have an open set which is a homogeneous space of the linear algebraic group. So for this case, this condition, well, it's not enough to have X over Q not empty, but if you put this condition, then there's a rational point. So this is proved in two steps by Sansuk and Brauer. Another case which was handled, which we find quite fascinating, is so conic bundles over the projective parameterized by just one parameter. Conic bundle over P1, that is a family A of t x squared plus B of t y squared plus C of t z squared equals 0. And then in the case when it has at most 4 bad fibers. So if you have a family of conics, the general fiber will be a conic, but of course there will be some special value of the parameter where the conic will break up like this. So you count the number of bad geometric fibers, and it turns out that, well, it's quite hard as soon as the number of bad fibers is big, but the case of 4 bad fibers is a difficult case. It's some analog of curves of genus 1, in fact. Just like curves of genus 1 are covers of P1 ramified at 4 points. And so in that case, we could prove that this condition is enough to ensure that there's a rational point. So the simple case is this equation, y squared minus az squared equals p of x, where p is a polynomial of degree 4 and a is a constant. Okay. Okay. And another case which has been proved unconditionally of this implication is if you take a complete intersection of two quarks in projective space when n is at least 8. And typically the technique which we use is stronger than the technique which the circle method would give. In fact, Brown told me once that he could prove this by the circle method over Q, but he couldn't do it over a number field, whereas the technique we use works over in a number field. I'm talking about this last result, not the previous one. I mean, there's no other technique to prove this for the time being than the one we found. Okay, so the proofs of this previous result use several techniques. One is something we call the Fibration Method. That is, we have a variety fibered over another variety into some nice varieties, and you try to reduce the Husserl principle to what happens to the fibers and the bottom. Now, this doesn't always work, because, for instance, for conic bundles, Iskowski has this example where you have a family of conic bundles. The fibers satisfy the Husserl principle. The bottom thing is P1, which is as nice as you could think of, but the total space doesn't satisfy. But nevertheless, one can do something. And the other technique is the descent method, where you have a variety and you assume that this set here is not empty, and you show that there is some auxiliary variety y which sits over x, which is much bigger, and which has a map from y to x, and which has points over locally, and which satisfy the Husserl principle. Then you reduce the problem downstairs to this problem upstairs. So these are the two techniques which have been used, which we've used at least. Okay, and then we systematically use class field theory, Nakayama, which is a generalization of this exact sequence I showed you before. Okay, and again, let me insist that we use the full statement. We not only use the fact that the composite is 0, which is what you use to prove to get counterexample. We use the fact that it's exact. That is, if we have element invariants with sum to 0, then they come from some global object on the left. And then we use the existing stock of varieties which satisfy the Husserl principle. We build our stock, and we try to create more. Okay. Now, if one is willing to grant certain standard, but quite difficult, very difficult conjectures, then there are many more classes of varieties for which we can prove this implication. So at least it gives us some hope that that makes sense. Okay, so if you assume the finiteness of Tate average groups, so for elliptic curves, there's a rich theory where people study curves which are over the algebraic closure are like elliptic curves, but which at the bottom only have points in all the completions. So for a given, I mean, you have to classify all this, but for a given elliptic curve, you look at all the curves which look like this given elliptic curve and which have points in all the completion, and they build up, this is a bit informal what I'm saying, they build up a group, a quite famous group called the Tate average group, for which a standard conjecture is that this group should be finite. So there are counterexamples to the Husserl principle in this context, but there should be finitely many ones. So a very difficult conjecture is that this group should be finite, and it's been proved for some elliptic curves. But for no algebraic, it's been from some arithmetic families, but no algebraic family. Okay? So if you assume this, so let's assume this finite of Tate average group, then this condition here implies this one. So this new condition with the Brauer group is enough to ensure there's a rational point. This was remarked by Manin in 1970 for any curve of genus 1. Then something which crept up more recently is the case of our curves of arbitrary genus. So if you take a curve of arbitrary genus with Jacobian as only finitely rational point, and you assume finiteness of Tate average group, then indeed we still have this implication. This is quite a strange theorem by Sharashkin. And then there are many diagonal cubic surfaces of a Q for which, if you assume simply this, you can prove that this condition is enough. So in particular, most diagonal cubic surfaces, as I said, where you have A, B, C, D, the coefficients, and there is no prime, and let's put it's strong, no prime occurs in two slots, then you will have modulo finiteness of Shah, you will have that there are rational solutions. This thing is satisfied. Okay. The other wild hypothesis which we've thrown in here, and quite often when we mention this, people react in horror, is the Bunyakovsky-Dixon-Schinzel hypothesis. Now, who knows about the Schinzel hypothesis here? Okay. Now it's very simple. So I'm going to. So at some point in the past, realized that Sasuk and I realized that. You remember that at the beginning I told you that that Husserl, to prove the Husserl principle for quadratic forms in 4 variables from the case of 3 variables, used Dirichlet's theorem and primes in arithmetic progression. And that theorem, Dirichlet's theorem, says that if you take a linear polynomial, x plus b, where a and b are co-prime, and a is positive, it represents infinitely many primes. Okay? Now you can ask, well, let me take x squared plus 1. Okay, it's not linear, it's irreducible. Does it represent infinitely many primes? Okay, and another question is, if you take 2 polynomials, like x and x plus 2, do you have infinitely many prime pairs? So people have, all these people, Schinzel, at some point, they said, well, Dirichlet's theorem should be just a baby case of a general theorem, or a general conjecture at least, if I take, say, an irreducible polynomial of arbitrary degree with integral coefficients, p of x, and you put some necessary, there are some stupid counterexamples. Say if I take x squared plus x plus 2, x squared plus x plus 2 is irreducible, but of course it's always even, so it's never a prime, well, except for x equals 0. But so there's some technical condition which I don't state, but the conjecture is essentially this: if you take a system, you take a family, a finite family of irreducible polynomials, you assume that some technical condition is satisfied. Well, there are infinite values of the parameters, so that P1 of x is prime, P2 of x is prime, PR of x is prime. Okay? So we're very far from having a proof of that statement. The best thing which people in analytic number theory can do these days is they show you that n squared plus 1 is infinite many times a product of at most 2 primes. But they never reached 1 prime. So nevertheless, this is a conjecture which people somehow believe. And so if you accept this, then you can mimic what Hasse had done starting from Dirichlet's theorem. And then you get lots of varieties for which you prove either the Hasse principle or you prove this implication. Okay? So, for instance, conic bundles of a P1 with an arbitrary number of bad fibers, that's okay. Okay? And this is exactly the generalization of Hasse's argument. So, I mean, it's a technical way, it's technical to do it, but the idea is just there. Okay, now if you put both conjectures together, then there are certain surfaces with fibration of P1 whose generic fiber is a curve of genus 1. So including some case resurfaces. So that's really quite surprising. So Sundar has written certain diagonal case resurfaces, AX4 plus BY4 plus CZ4 plus DT4 equals 0. And then it's really very surprising because at first you wouldn't have even dared to conjecture that some version of the Hasse principle should be true for surfaces whose geometry is that complicated. Okay? They are very far from generalizations of conics. Okay, and also under these two conjectures, you can prove that for most smooth integers of 2 quarks in P4, the Brauer-Manin condition is enough to guarantee rational points. And in fact, you can prove a very simple statement under both conjectures that the Hasse principle holds for smooth integers of 2 quarks in Pn for n at least 5. So you should compare with what we've achieved before. Unconditionally, we have n at least 8. So the conjecture is that it should be okay, the real Hasse principle, local solutions everywhere implies local solution, as soon as n is at least 5. So at least as you have 6 variables for 2 quadratic forms. And so Wittenberg proved this in his thesis. Okay, so some numerical support for this implication. It exists for diagonal cubic surfaces, so this is something we did quite some time ago. And more recently, there's something surprises has crept up, is that people have started conjecturing that this implication, which is quite reasonable for curves of genus 1, should also be true for curves of arbitrary genus. And I can tell you that 10 years ago I would have thought this is totally crazy. Bruin and Stoll have discussed simple curves of genus 2. Y squared is a polynomial of degree 6. And they've searched, so I mean the techniques, well actually of course this condition looks complicated. So there's a translation of this in terms of certain congruencies with the Jacobian. And so these people know very well how to compute with the Jacobian of curves. And they've looked at families of equations like this, and they've seen whether this condition is satisfied or some version. And at the same time, they're looking for small rational solutions with, you try x and y of the shape P over Q, where P and Q are small in the computer, and you look for solutions. And you look for solutions in a clever way. That is, if you have congruence conditions, of course, you're going to put them into the computer. And so they really have some numerical evidence for the conjecture in this case. There's also some numerical support for some Shimura curves, so we can put some technique from Shimura varieties. And also for some case resurfaces, in particular diagonal ones. So Sundar and Bright have some numerical evidence. But, because this is the next point, one should not jump to conclusion. This implication does not hold in general. Okay? So I remind you, in 1970, Manin coined this condition as a necessary condition for the existence of rational point. And then for many years we were producing varieties, well, some varieties, for which we could prove this implication. And we never believed that this implication should hold for any type of system of equation because it would contradict in some way Lang's conjecture on variety of rational points and variety of general type. But it would contradict some conjecture, so we had no counterexample. Okay? But in 1999, Skorogatov gave the first unconditional example of a variety, in fact a twisted bielliptic surface, which has this condition fulfilled but has no rational point. So there was a new obstruction which was discovered some 30 years after Manin had defined his obstruction. Yeah. And the technique has been analyzed by these people. And so I mean, if you want to caricature the difference, is that when take into account Galois and ramified covers of the variety whose Galois group need not be commutative. So the obstruction coming from the Brauer group, you can reinterpret it in terms of covers of X, which are homogeneous spaces under some commutative groups. And so there was a shift to torses, as one say, under non-commutative groups. So this was the interpretation of Skorogatov's example. Okay? And they're also interested in for analysis of rational points and curves, as Stoll has shown. Okay, but then the next step is that in, well, actually, so Skorogatov is a beautiful example where this condition is not enough. And Poonen, quite recently, find a new example which is not accounted by this. Okay. So it's one step more. This variety with this condition is satisfied, but there's no rational point. But these techniques, using unramified covers with a Galois group, say a finite group, do not work. Okay. So this is the situation right now. Okay. Now, I'll say a few words about integral points, but anyway, I mean, I think rational points I wanted to cover anyway. So look at the integral Brauer-Manin abstraction, which I defined at the beginning. I look at a very concrete family of examples. So these two people, Xu and Schulze-Pilow, they produced, in fact, I was at a conference in China a couple of years ago, and Xu was giving a talk on this, so I said, oh, well, that's interesting. So look at nmk positive integers, nm coprime, and look at this very simple equation. So you can call it a scheme if you want, but you can ignore the word scheme. You look at this representation of 1 by this ternary quadratic form. X, Y, Z are the variables, and M, N are fixed. Okay? Which you can also rewrite like this. A product of two linear terms equals this quadratic term. And so Xu and Schulze-Pilow studied the integral solution of this equation, that is, whether 1 can be represented by this, depending on the value of M and N. Okay? And so if you apply the Brauer-Manin method, one checks that in fact there are always solutions locally. So we want to try to apply Brauer-Manin. So first we discuss the local solutions. So there are always local solutions. So what about the Brauer obstruction? So now here's what you do. You look at the open set of this variety here, which is defined by the fact that one of these terms doesn't. You look at the open set where this is non-zero if you want. Okay? So you have this function 1 plus nky, and you check that the quaternion algebra 1 plus nkyn, which a priori is an Nassian algebra over the open set where this is non-zero, actually extends to a Nassian algebra over the whole of the previous equation. Okay, so over the whole this whole thing. So this is some algebraic checking, and you check that it spans the quotient bar by xq divided by bar of q. And now you start evaluating this element on the various x of zp. You find that for p different from 2, whatever n and m are, this A vanishes on x of zp. And then for p equals 2, there's a discussion. And so the image of this map is 1 over 2, or it is just 0. So it is 1 over 2, that is different. It coincides with just 1 over 2, if and only if 2 divides m exactly, that is the m is divisible by 2, not by 4, and n is congruent to 1 mod 5. 4 divides n, and n is congruent to 3 or 5 mod 8. Now, this is a purely two-adic computation. Okay? We've looked at p, then we looked at 2. We've done this purely two-adic computation. And so what we conclude is that in case 1 and 2, we conclude that this set here is empty. Okay? Because on the p different from 2, you get 0. But at p equals 2, in these two cases, you get 1/2. So the sum, if you sum, you get 0, 0, plus 1/2, non-zero. Therefore, there is an obstruction. So there is no integral point. Right? So you apply the Brauer-Manin method, and you discover that in these two conditions, if either one holds or 2 holds, then there is no integral point, even though there were local points in ZP for all p. Okay, now, what was remarkable, of course, Xu and Schulze-Pilow had proved this, not using the Brauer-Manin language. But they had proved that in all the other cases, there is an integral point. So this was a surprise. So it turned out that this condition, this Brauer-Manin condition, seemed to be the only one. Of course, at the time, they were not using this language at all. They were using the language of genus theory, which is a classical language going back to Gauss, and which for me is very complicated. This is something to discuss integral quadratic forms. And so the question was, is this a special case of the general theorem? So are there classes of scheme X over Z for which we have this implication? Of course, with integral points, we have to be less ambitious than with rational points. Okay? And so you make a modest start. You look at P1 minus a point. Okay? You start with the simplest variety. Okay? So here's a nearly trivial result. So you take A, B, C, and Z not holds 0. You look at the equation X plus BY equals C. So if the solution holds ZP, then it's a solution in Z. Okay, that's not too hard. But it's not completely obvious. I mean, it's a strong approximation theorem. It's a Chinese remainder theorem in some form. Okay? And here, the equation, of course, is XQ is equals to P1Q minus infinity. Okay? So if you compute the Brauer group, there's no obstruction. And in fact, it is a fact. There's a local global principle here. Okay? In fact, the strong approximation theorem gives a stronger result. It says that the integral points are dense in this product. They're dense in this product, but we omit the reals. It would be wrong if you put the real as well. Okay? Okay, now you look at the next step is P1 minus 2 points. And now look at the Z curve defined by this equation. Okay? Then you find that it has solutions in all ZP, but not in Z. Just check. I mean, because xt is 1, there are not many solutions in Z again, so it's very easy to do this. And in this situation, over the rational, that curve is isomorphic to P1Q minus 2 rational points, 0 and infinity. And here, in fact, the Brauer group is all enormous. See, the Brauer of P1 is trivial, but the Brauer of P1 minus 2 points, that's an enormous group. It's a group of characters of the absolute Brauer group of Q. And in fact, one can check that there's a Brauer-Manin obstruction attached to this quaternion algebra. Okay. Now, in a not completely immediate fashion, if you use classical Colliot theory, in fact, Harry proved, and it was not obvious to me, I must say, that if you take a scheme X, which over Q becomes isomorphic to P1 minus 2 points, and so you have P1, so P1 minus 2 points could be of two ways, P1 minus 2 rational points, or P1 minus 2 conjugate points. Okay, we look at these two cases. Then in that case, this implication holds. So this holds in particular for equations like A equals Q of xy, where say Q of xy is not a factor of two factors. It's irreducible, okay, corresponds to these two conjugate points. So in this case, this implication holds, which is quite comforting. It's comforting except for one thing, is that this group is so enormous that it's impossible to check this condition. But theoretically, the result holds. And now this is something which is not to be completely despised, that is, you can imagine to prove that's a principle for a variety which is fibered over, say, P1, using a statement like this for the fibers, when the Brauer of the total space is very small, but the Brauer of each fiber is enormous. And you can, if you can reduce to something at the fibers, even though this is not to be computed for a given fiber, you could use you could prove the theoretical result which would be useful for the total space. Okay? So anyway. So difficult for application, this group is infinite, okay, and so it's not easy how to decide this. Okay, there are some special results. So for instance, this result of Cox, which I mentioned at the beginning, is a case where you have a technique. So where you should have thought about which cases can be handled in a similar way. Okay. And now this really improves if you look at the problem of representational integer by an integral indefinite quadratic form in 3 variables, q indefinite. Okay. In that case, if you look at a equals q of x1 xn, if n is at least 4, the quotient here is 0, and if n is 3, the quotient is at most n mod 2. So that the computations are finite for the Brauer-Manin obstruction. Okay. And the theorem is this: if you take an integral quadratic form of rank n, indefinite over the rails, and you take an integer, I said indefinite, yeah? If n is at least 4, then there's a local global principle. In fact, that theorem, as I say in the next slide, goes back to Eichler and Harder. And for n equals 3, and this technical condition, the bar group here is n mod 2. You take a generator, and you have a way to, you just look at this map into q mod z, as we saw, in, similar to the example we saw at the beginning. And you find that this set is non-zero if only if 0 is in the image of this map. And what is amusing, so A goes back to Eichler, Kneser, and Watson, and B is a variant of Borrower and Rudnick. Okay? And the main points are something called a strong approximation for a spinor group, and then the fact that the quadratic like this can be viewed as a homogeneous space of a certain algebraic group over Q. And something I will probably finish here is to know that you can actually do the computation. So I remind you, we're discussing whether an integer can be represented by a ternary quadratic form which is indefinite. So what you do is that you suppose you have solution in all ZP. So by the classical Hasse theorem, you know that there's a representation of a Q. So there's a rational solution for this, x, y, z rational. So you find a rational point. People have technique to find an explicit rational point. And then you do something very simple. You write the equation of the tangent plane at this affine quadratic at this point. And then you look at this quaternion algebra, L of x, y, z. So from this rational point, you deduce the equation of L. And then you apply the mechanism I said before, evaluation on p points. And that's the algorithm to decide if an integer is representable by q of x, y, z. Okay? And you get in this